Hi guys, in this lecture we are going to extend our discussion of atomic structure by introducing the concept of orbitals. So the concept of an orbital addresses one of the basic questions that many students have as soon as they see this model of an atom. Namely, the question that is asked is, why is it that if you have protons that are positively charged in this nucleus and electrons that are negatively charged around that nucleus, why is it that those electrons don't just simply spiral in and crash into that nucleus, right? And this is a problem that arises with a simple orbit model of the atom that's illustrated here, right? And it's found its way into the hearts and minds of many science students, and it's well represented in the popular media, but it is actually a completely incorrect model. In order to properly describe the behavior of electrons around a nucleus, we need to abandon the idea of orbits and look at this concept of orbitals, which essentially describe the electrons as existing in these smeared out regions of space around the nucleus that define the probability of finding the electrons in a given region. And that's the definition that I want us to move forward with in this introductory lecture, right? So I want to define orbitals as these regions of space where electrons are likely to be found, right? And so there's a bunch of different types of orbitals, right? And each orbital has a definite shape, size, and energy. Okay? The four orbital shapes that we are going to be working with are illustrated here on this slide. And each one of these shapes has a corresponding letter designation that allows us to quickly reference that particular orbital shape or orbital structure. So the first one here is a very simple structure denoted by S. We'll call this an S orbital, where you basically have a region of space defined as a spherically symmetric distribution around that central nucleus. So you can picture, a little dot right in the middle of a big sphere, like a big beach ball or something, right? And that is defining the region of space around that nucleus where you're likely to find the electron. Okay, now if you move to the p-type orbitals, it turns out that the structure of these orbitals gets a little bit more interesting, right? As you can see here, rather than having a single sphere like we do for the S, we now have two spheres, and these spheres are touching right at the nuclear position, okay? And so this sort of two-lobe structure for the p orbitals is sometimes referred to as a dumbbell shape, right? So p orbitals, our second orbital type, have a dumbbell shape. The third orbital type that we'll talk about here is the so-called d orbital, which has something of a cloverleaf appearance, where we now have four lobes, okay, with the nucleus right there in the center, and so on and so forth. And in fact, there's no limit as to how many lobes that you can continue to add on, and you continue to add on new designations for these guys. For our purposes, we are actually really going to be focusing in on only these first three types of orbitals. And so what I want you guys to be able to do is, pick from a lineup the correct orbital shape for any one of these S, P, or D orbitals. So if I put a picture up there, I want you to identify from a lineup of one of these three images which one is S, which one is P, and which one is D. Okay, and if you can do that, then you've got orbital shape down. Now let's move on to size. So the orbital size, right, is related to essentially how far out this sphere goes, or this region of space goes, away from that nucleus. Okay, and it turns out that for orbitals of a given shape, so for example, we'll look at just S orbitals here, so all spherically symmetric orbitals. These orbitals of a given shape can come in different sizes. And we're going to denote these orbitals of a larger size by a larger number in front of that letter designation. And we're going to call this number the principal quantum number, okay? Oftentimes denoted by just an n. So the principal quantum number for the smallest s orbital is 1. The principal quantum number for the second smallest s orbital is 2, 3, 4, 5, 6, and again goes up without bound. And each time you increase that value of n, you get a larger and larger orbital. Now the same thing happens for our orbitals of our different shapes, right? So for example, if we look at the p orbitals, if we increase the value of that principal quantum number for the p orbitals, we get larger and larger p orbitals. But again, the basic shape of the orbital does not change. It's just its relative size. And so basically the likelihood of finding an electron further away from the nucleus increases as you go to these higher values of that principal quantum number, okay? And I'll draw your attention as well to the fact that when we are looking at p orbitals, the smallest principal quantum number that we start off with here is in fact 2. So we're not starting at 1. And again, the details of this is something that I direct you guys to my more advanced lectures, for general chemistry, if you're interested in knowing the details. But for right now, I want you to just have in mind that there's this principal quantum number n, and as you increase the n, the size of the corresponding orbital increases. And last, we'll look at the same trend for our d orbitals, right? Now note that we are starting at an n equals 3, but the same sort of story holds, right? Higher n, larger orbital size. Okay, now we're ready to move on to our final discussion, which is the discussion of orbital energy. Okay, so it turns out that for a given principal quantum number, orbitals with a greater number of lobes have a higher energy. So for a given n, we'll fix n, the energy of a p orbital is greater than that of an s. The energy of a d orbital is greater than that of a p. And the energy of an f orbital is greater than that of a d, right? So for a fixed n, you can remember more lobes, more energy. Now there's another trend as well. What happens if we are looking at a succession of progressively larger orbitals of a fixed shape? So if we go back to our s orbital example, 1s, 2s, 3s. Well, it turns out that energy increases with the principal quantum number. So higher n has a higher energy. So higher n results in larger orbitals with a higher energy. And to sum this up, what we typically do is represent these different orbitals using a so-called energy diagram, right? And this energy diagram places on the y-axis increasing energy, and we start off then with our lowest energy orbital. In this case, it would be our 1s orbital. And then we go up to our next lowest energy orbital, which is 2s. And then remember, once we get to n equals 2, we start having these p orbitals show up. And these p orbitals, right, it turns out that there's 3 different orientations that these p orbitals can take, 3 different distinct orbitals, all with the same shape. And all 3 of these p orbitals have a larger energy relative to the 2s. Because remember, more lobes, more energy. Then you go up to the next principal quantum number 3, and we have an even higher energy. And then the same sort of trend follows. Okay. Now, for the purposes of this class, that's a sufficient level of understanding to basically, to solve the problems at the introductory level. I will, however, make note at this point that when you are building up these energy level diagrams, right, there's other trends that come into play. And for example, we find that the energy of the 4s orbital, it turns out it's oftentimes a little bit under that of the 3d. Okay, So there are some subtleties to this diagram, and you will see that if you're looking at other textbooks and the like. But once again, to explore those in more detail, I'm going to direct you to the more advanced work. For the introductory concepts, I want us to really just focus in on this basic orbital energy diagram, looking at these trends of increasing energy with increasing N and increasing energy with increasing number of lobes. Okay, so that was a lot of new material. Let's do a quick recap. So first and foremost, right, electrons live in orbitals, right? These regions of space around the nucleus and that describe the likelihood of finding the electron in this region. Orbitals are defined by a specific shape, size, and energy. We designate different orbital shapes by a letter, S, P, D, F, G, and so on and so forth. We're going to be focusing in on the first three. Orbitals of a given shape, but different size, and as we saw, energy, are denoted by a different principal quantum number n. And we saw that larger n corresponds to larger orbitals, and larger n corresponds to higher energy orbitals. In the next video, we are going to explore how we can use these concepts of orbitals along with a handful of, really 3 simple rules to allow us to describe the electron configuration of any atom on the periodic table.